Hello dear audiences, this is a Statistic and Probability for Engineers Part 7 and I am Mohammad Momenzadeh, the presenter of this lecture. So in this lecture we will discuss about the multiplicative rule that is derived directly from the concept of conditional probability, and moreover we will discuss about the Bayes rule, the most important rule in this topic. I mean, most of the computer and the machines work with that rule. The Bayes rule is too basic, but it's too essential, and later on you will see that how can we use this type of the things in our real life as well. So let us take a look at the multiplicative rule that is derived directly from the conditional probability. So before that we go into the multiplicative rule, it's important to understand the meaning of independency for two events. I emphasize about the events over here, that we talk about independency of events. We have the concept of independency for the probability distribution function as well, but right now we will talk about the events, and for two given events A and B, they are called to be independent if these two condition holds true. This states this type of the formula. I mean, both of them are equivalent to the next one, that the probability of their intersection should be as the same as multiplication of their probability. Indeed, this formula is coming from this concept. As you remember that the conditional probability of A, given that the B is it has been already done, was equal to the probability of their intersection. If you remember that, I said it to calculate the conditional probability, you curve the vertical line to the shape of the intersection, then it's as the same as intersection of A and B, probability of A intersected by B, over the probability of the second one. So if we write this conditional probability, then these two events A and B are independent if happening of one is not affect the another one. So by the another word, probability of A in a condition of B should be equal to the probability of A. So if it's as the same as the probability of A, then the happening of events B is not affect the probability of A. Also, if they are independent, the happening of A cannot affect the happening of B. So I can say that the probability of B in a condition of A, that type of the probability should be as the same as the probability of B at the end. So it should be as the same if they are independent. If two events are independent, this is the condition for them. And as you remember that this conditional probability can be presented by the probability of their intersection, means that B intersected by A over probability of the second one, which is probability of A. And by these things you can see that this condition means that the independency of A and B reach to this formula, that the probability of their intersection, probability of A intersected by B, should be as the same as multiplication of their probability. So if I just multiply both sides of the first expression by probability of B, then the probability of their intersection, as you can see, should be equal to the probability, to the multiplication of their probability. And this should be true for the second one as well. So means that both of them reach to the same thing, and this condition determines the independency of two events. One of the things that mislead the students too much is about the independency and mutually exclusive. Indeed, if we have two mutually exclusive events, means that there is no intersection between them. They are disjoint, and for sure these two disjoint events are dependent, not independent. What do I mean? So assume that A and B are disjoint or mutually exclusive, then there is no intersection between them, so the probability of their intersection means that A intersected by B is as the same as the probability of empty set. And based on an axiom of probability, the probability of phi or empty set is equal to 0. Of course, if these two events are not empty, they are not actually impossible events, then I can say that the probability of A times probability of B will not be equal to 0. So it means that these two probability are dependent, they are not independent. That's things that most of the students made a mistake about it. So it's not equal to 0, of course, if one of them is not 0, so or not impossible. So the case say that two mutually exclusive events are dependent indeed. So let us take a look at the next slide. It's about the multiplicative rules, and it's this formula is coming out directly from a definition of a conditional probability. As you can see over here, I wrote the conditional probability for probability of A in a condition that the B has been occurred, and it's equal to the intersection of this probability over the probability of the second event. The probability of B in a condition of A, or A is given, it's equal to the probability of their intersection over the second probability or the probability of A. And if I multiply the first expression by probability of B and second expression by the probability of A, then I can find the formula for the probability of A intersected by B. So as you can see, probability of A intersected by B is equal to the probability of B times probability of A if B has been happened. And also you can write it as a probability of A times probability of B where A is given. In a case that two events are independent, we can say that the probability of A intersected by B is as the same as multiplication of their probability. I want to emphasize about this formula that you can apply the multiplication rule only if two events are independent. Otherwise, you cannot apply this formula for the given cases. So there are several examples for multiplicative rule and how can we use the multiplicative rule. Here I want to introduce one example, and later on I will make that example more difficult, and you can see how can we use that actually concept to calculate the probability of a given event. So let us take a look at this example. As you can see, we have one question here. There are two bags in this question. One bag contains 4 white balls and 3 black balls. That I sketched that bag over here, and you can see it over here, that one ball unseen transfer from the first bag to the second one, which contains 3 white balls and 5 black balls. And at the end of the day, after that we transfer that ball from the first bag to the second one, we draw 1 ball from the second one, and we want to know that what is the probability of getting the black ball from the second bag. So this is the question. And before that I solve this question, I want to just show you something. First of all, there are 2 possibilities for transfer ball from the first bag. Means that I can choose the white ball or I can choose the black ball. Because we have 4 white balls over here out of 7 cases or 7 balls, totally 7 balls we have in a first bag. So the probability of getting a white ball from the first bag is 4/7, and the probability of getting black balls is 3/7. Means that with the probability of 3/7 we can transfer the black balls to the second bag. With the probability of 4/7 we can transfer the white balls to the second bag. At the end of the day, when I transfer the ball to this bag, the number of the balls becomes 9 after that I transfer it. Means that when I transfer the black or the white ball to the second one. So right now, to determine the probability of getting the black balls from the second bags, that we denoted by B2, means that I'm looking for the probability of getting black balls from the second bag. I can say that I can split the space or the sample space to two parts. It could be transferred the white ball from the first bag, or it could be the black ball which is transferred to the second bag. We have two cases, so in both of cases we can solve that question. Indeed, this B2 or getting the black balls from the second bag is equal to the probability of getting the second the black balls transfer from the first one, and we get the black from the second one. So it can be like this, or when we put or, means that we have a union by transferring the white ball from the first bag intersected by the black one from the second one. So that means we have two cases indeed. Our space over there, our sample space over there can be split to two parts. Means that we can transfer one of them with the black balls, means that the first transformation is a black ball, or the first transformation can be the white ball. In both of the cases we have these things. So as I said it, the space is split to two parts. One part that the black balls is transferred, one part that the white ball is transferred. And if I consider the events of B2 over here, as you can see, this B2 split between these two parts, and I can say that there is two parts over here. One is the intersection of B2 and B1. As you can see, the B2, the set B2 over there is their intersection. This black part over here is the intersection of B2 and B1. Let me just write it, B1 and B2 intersected by B2. And the another blue part that I have it at the right side is a intersection of B2 and W1. So the B2 totally is a union of these two intersections. So it could be transferred the white ball from the first one, or it could be the black one. So the B2 or getting the black balls from the second bags is split by these two actually events, W1 and B1, and as you can see, it's a union of these two things. And based on an additive rule, I can say that this union can be seen as an addition of their probability if they are disjoint. And as you can see, because it's a split like this and there is no intersection between these two spaces, so I can rewrite them as the addition of the probability. I emphasize about that because there is no intersection between these two events. The first one is here and the second one is there. There is no intersection between them, means that it cannot be possible to transfer the white and black balls in the same time. So there is no intersection between two spaces. So the probability of their union based on additive rule right now is a probability of the first one that I wrote it over here plus the probability of the second one. So let me just write the second one as well here and transfer that things as well. So if I just write it over here, it's a probability of the second one plus the first one together. So this is the addition of their probability, because we had the union of two probability, and this is the additive rule. Right now, the probability of each are the intersection, and I can write them as a conditional probability. It will be equal to the probability of the first one, probability of getting black from the first one, because we have already known that what is that probability. We calculated before, it was 4/7. We found out that the probability was 4/7 times probability of getting black from the second one, in a condition that the black one is transferred for the first one, means that B2 in a condition that the B1 was happened. So plus the probability of getting white from the first one, times probability of getting black from the second one, if the white was the transfer ball over there as a first one. So the probability of B1, as I said it was equal to 4/7, and if I transfer the black ball, the first one is a black, and I transfer the black balls from the first to the second, then the number of the black balls over here means that I transfer the black balls to this one. So this is the black ball here. If I transfer it here, then the number of the balls becomes 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. And the probability of getting black will be 1, 2, 3, 4, 5, 6/9. So it will be 6/9. 6/9. Also, the probability of getting white from the first one is gonna be 4/7. White is 4/7. I made a mistake. It should be 3/7. The black from the first one, it was black. Okay, so it will be 4/7 right now. And probability of getting the second one black, if the first transformation was white, again we have 9 balls after that things, and we have right now 5 blacks, so it will be 5/9. So this calculation lead us to the value of 38/63. So I just like this question, and in a midterm exam most of the time I just made a question, modify the question and make it more complicated. Let us take a look at a more complicated example about this case and see how can we solve that type of the question. So as you can see over here, I modified the question a bit, and we have the another example over here based on that modification. As you can see, we have 2 balls again. Let me just use that marker. So as you can see, we have 2 balls again over here, and the first ball contains as you can see over here, the first ball contains 1, 2, 3, 4 white balls and 3 black balls. The second bag contains 1, 2, 3, 4, 5 blacks and 3 white balls. And right now, instead of transferring only 1 ball from the first bag to the second one, I transfer 2 balls from the first bag to the second bag. And then I ask you to find the probability of having 2 balls, 2 black balls, when I draw 2 balls from the second bag. Right now I want to solve this question. This is totally, the logic of the question is totally similar to the previous question, but at the exam the student challenged too much with that type of the questions. So right now I can say that our sample space is divided to 3 parts, not 2 parts anymore. So there is 3 possibility for a transfer balls from the first bag to the second one. What do I mean 3 cases? Means that I can divide the space to 3 parts. One part is a transferring of 1 black and 1 white. So I can transfer 1 white and 1 black balls from the first bag to the second one. Or simply I can transfer 2 white balls from the first to the second one. Or in the third case, it may be both black, means that I can transfer 2 black balls instead of 1 black or 1 white to that one, and the probability of each case are different as well, means that the probability of each can be calculated. Let us calculate that one. So for the first case, let me just write the case over here by small a and small b and small c, so it's easier to calculate it. To calculate the probability of a or small a, let us use that events by the lowercase alphabet. It's normally you should use the uppercase. Let me just use the uppercase alphabet as well to avoid that type of the problem. So I just named the first one as E1, the second event as E2, and the third event as E3. We have 3 events over here, and let me calculate the probability of each. Probability of transferring 1 white and 1 black from the first bag. I want to calculate that one. So right now, because it's a group of balls that I transferred, and the order of the elements or the balls are not important, I should use the combination. You cannot use the permutation in this case. So I should evaluate the number of all cases. First of all, we have 1, 2, 3, 4, 5, 6, 7 balls totally at the first bag. So we have 7 balls at the first bag, that 2 of them are drawn from the first bag. So it's a combination of 2 out of 7. This is the total cases that we can consider it over here. 2 out of 7, and the probability that I look for it is a probability of getting 1 white and 1 black, means that one ball should be selected out of 1, 2, 3, 4 white black, multiplied by the selection of 1 ball out of 3 cases. So this is the probability of E1, and let us calculate it. So it will be 4 times 3. The numerator will be 4, and the next one is 3, and the denominator is 7 times 6 over 2, or 21. So it will be, the result will be 12 over 21. This is the probability of getting 1 white and 1 black. 12 over 21. The probability of getting 2 whites means that the probability of E2 of getting 2 white balls is equal to, again, the denominator of that case is as the same, is 21. But as you can see, I should collect 2 white balls out of the white cases, means that 2 out of 4. So 2 out of 4 is 4 factorial over 2 factorial over 2 factorial, or is equal to 6 over 21. And the probability of E3, or the third event, that we getting both of the balls as black balls, is equal to selection of 2 out of 3. So it will be 2 out of 3. The denominator should be as the same, is equal to 21. So it's 3 factorial over 2 factorial, which is 3 over 21. So as you can see over here, as you can see, the addition of this probability also should be equal to 1, means that 12 over 21 plus 6 over 21 plus 3 over 21 is 9. 3 over 21 will be 21 over 21, or 1, because it's cover the whole space. So the whole space or possible cases is equal to the addition of them, means that we have 3 cases for 2 balls that drawn from the first bag and transferred to the second one. We have 3 cases, and we calculate the probability of all possible cases over there. So that's the reason that we can write it over there. So after this step, I should consider the case of getting 2 blacks from the second draws, and if I choose that set, that events as a let me write it by B2. B2 is an event of getting 2 black balls from the second one. So this B2 can be splitted by 3 parts right now. 1 part for the first, 1 part for the second, and 1 part for the third case. Means that by the another word, I was looking from very beginning to calculate the probability of B2, means that getting 2 black balls from the second bag. And this probability of B2 should be equal to the probability of B2 intersected by E1, B2 intersected by E1. This is the green part at the shape that we have it. Union by, this part should be union by the B2 intersected by E2. So this is the blue parts in a shape, and at the end you should add or make a union by B2 and E3, the purple part over there, means that B2 intersected by E3. And over here, as you can see, these 3 sets means that the first one, the second one, and third one has no intersection. So because of that, I can rewrite that one as an addition of these probabilities. Based on an additive rule, I can write it as an addition of these probabilities. So this is the addition of these 3 probabilities, and all of them are intersections. To calculate the intersection of 2 events, the probability of intersection for 2 events, I can use the multiplicative rule, and it's as the same as probability of E1 times the probability of one of them times the probability of the another one. If the first one has been occurred, means that probability of B2 over here, when we know that the E1 has been already happened, it's as the same for the remained. So we have the following things. So now we know what is the probability of E1. We calculated before that what is their probability. It was 12 over 21. But what is the probability of B2 in a condition of E1? Condition of E1. E1 was 1 white and 1 black. Means that if I transfer 1 white and 1 black to the second bag, then I'm looking for the probability of getting 2 blacks when this transformation has been happened. So as you can see, it will be equal to the multiplication of these cases. Means that we have right now I want to get 2 blacks, so 1 2 3 4 5 6 black totally we would have it over here. So it will be 2 over 6, 2 out of 6, the combination of 2 out of 6. And the total cases that we have it, because 2 balls transferred, totally we have 1 2 3 4 5 6 7 8 9 10 cases. So we need 2 out of 10 over here. For the next one, for the next case where we have the probability of E2, it was 6 over 21, and we multiply that value by the probability of B2 in a case of E2, means that both of them will be white. If both of them will be white, means that this balls also is white, then the number of the white balls will be reduced. Then we will have only 5 black balls, and these 2 balls should be chosen out of that 5 cases. And again, the denominator is as the same, 2 out of 10, the combination of 2 out of 10. For the last case that we have 3 over 21, means 2 black are transferred. If both of them are black, then the number of the black cases will be, black balls will be 7. So I need to collect that 2 black balls out of 7 cases, and the denominator again is the same. So we have 2 out of 10 in a denominator as well. So with that calculation, you found out the probability of given case. However, the logic are the same. It seems that to be more difficult than the previous one. So let us take a look at one favorite question, my favorite question in midterm exam, for instance. Over here we have the electrical circuit and we have 4 switches, one A and the another one B, C and D. And the question is as follow: if probability, the events A defined as a probability of switching A, and B, the events B is a probability of switching that connection B, and so on for C and D, and this relation holds true, they ask you that what is the probability, which lamp over here will be turned on, the most possible case for turning on, which one has the most likelihood to turning on. This is the question over here, and we want to know that how can we switch it on and which one is most possible. For the orange color lamp, we have 2 switch. If A and B, both of them in the same time will be switched, then the orange lamp will be turned on. So the probability of getting the lamp, the orange lamp, is equal to the probability of A intersected by B, because both of them means that A and B, both of them simultaneously should be switched on to turn on the lights of the orange color. So over here the probability of A intersected by B, because A and B are independent based on the information that is given in a question, because they are independent, I can rewrite their intersection as a multiplication of their probability. It was the definition for the independent probability. To calculate their intersection, I can multiply them if they are independent, and it will be the probability of A times probability of B, and it's gonna be 0.8 each of them, so the result is 0.64. so the probability of turning on the lamp orange is equal to 0.64. For the yellow color, we have the probability of C intersected by D. That's gonna be the probability of turning on that light. So C intersected by D can be written as, because the probability of D when C is given over here, it's give at the question, so it's 0.75. D and C are dependent because there is some conditional probability over here, and the intersection of them can be written as a probability of C times probability of D. C is given, or probability of D times probability of C. D is given, but here the probability of D where the C is given as an information is given in this question. So for this reason I can rewrite that one as a probability of C times probability of D times probability of D where the C is given. Also you can rewrite that one as a probability of D times, let me just rewrite it over here. So you can rewrite that one as a probability of D times probability of C where D is given, but we don't have this information. The second information is not given in the question, so I will follow the first information. Probability of C is given is 0.9, and probability of D in a case of C is given, so I multiply that value by 0.75. As you can see, one information is useless over here for this case. So by calculating that value, the multiplication of them, if I just use the calculator over here, 0.9 times 0.75 is 0.675. So for sure the probability of the second one is more, so this light is most possible to be turned on, because the value of the probability for the second case is greater. So most probably the yellow light will be turned on for this case. We may have the same situation for a hydraulic and powers in a dam as well, with some switch. So let us take a look on that case as well. So as I said it before, I can change the question. Instead of the electrical circuit, I can talk about the water. Assume that this is a apparatus of getting the water inside and getting out the water. I mean, the water is coming from this side and there is 4 gates, A, B, C, and D. And the question is about that in which way we have the most possible situation to pass the water. And as you can see, based on given information, if the same information are given, means that this information are given, you can see that the most possible way for the water is a second way at the bottom. So we can change the values and change the conditions, but the situation and this system or apparatus of the water are the same actually. So let us take a look at the next example. As much as you solve more example, it can be help to be expert in that field. So we try to solve as much as we can in this course. So right now the next example is about the cards, playing cards deck and the playing cards. So it's necessary to know a bit about the playing cards. Indeed, the origin of the probability return back to the gambling, and this type of the issue was the inspiring things for stating the probability. So over here we have 52 cards, as you can see at the shape on the right side. We have 52 cards. They are the playing cards. It's divided to 4 type of the cards. One, diamond. Diamond has a shape like this. I mean, the first type of the diamond, the cards over here are diamonds. So these cards are diamonds. Then we have a club as well. These are the club cards, and the another one is a heart and a spade. So we have 4 type of the card in a playing cards, and a deck of the cards contain 52 cards. So means that these 52 cards divided to 4 type, as I said it, the diamond, the heart, the club, and a spade. And for each of them we have 13 cards, means that we have 13 cards of a diamond, 13 cards of a club, and 13 cards of the heart, and 13 cards of a spade. And it contains the number 1 up to 10. The number 1 is called the ace. So you can see the ace over here. And then the number from 2 to 10. So it's 2, then 3, 4, 5, 6, 7, and 8 over here, 9 and 10. Then we have 3 more different type of the cards that are the jack and the queen and king. So these are the playing cards, and the question is about that playing cards as well. So they said that 3 cards are drawn in succession without replacement. It's important, this part, that the replacement is not allowed. If I have the deck of the cards over here and I draw a card and I replace it back, then choosing the second card will be independent from the first one. But if the replacement is not allowed, like this example, then the situation is different, and this type of the events, I mean choosing the cards or drawing the card from the deck, is dependent, because the second card that you choose it when the replacement is not allowed. Without the replacement, I want to talk about this case. If the replacement is not allowed, the second card is totally related to the first one. I mean, choosing the first one can affect the probability of the second one. They ask you in this question to calculate the probability of the intersection of A1, A2, and A3, where A1 is a event that the first card is a red ace, and as you can see we have 2 red ace over here. One of them is heart and one of them is diamond, so we have 2 red ace, and the probability of that one of course will be 2 over 52, means that the probability of A1, the probability of getting 2 red aces will be 2 out of 52, because we have 52 cards and we have two red aces, the diamond and the heart. So the A2 is an event that the second card is a 10 or jack. So if you just take a look at this playing cards deck, then you will find out that the jack, the number of the jack are 4. So we have totally 8 cards of 10 and jack. I just circle it over here. You can see over here the circle that I put it. It contains 8 cards. So the probability of A2 is gonna be 8. Probability of A2 without considering A1 or anything else will be 8 out of 52, 8 over 52, not 51 indeed. So it's gonna be 8 over 52, and A3 is a probability, is an event that the card is is the event that the third card is greater than 3 but less than 7. So it's not inclusive, the 3 and 7. So the number between 3 and 7 is 4, 5 and 6, means that we have these cards over here. So I circle it over here. These cards over here are between 3 and 7, and 3 and 7 are not included in that cases. So as you can see, we have 3 rows of cards, and each row contains 4 cards. So 3 times 4 will be 12. So A3, the probability of A3 is 12 over 52. But they ask you to calculate the probability of their intersection if we have the replacement, and the replacement are allowed. As you can see, there is no intersection between these cards, between 2 aces that located in the middle. You can see it over here. They located over here. Let me just use the another color. I use a lot of arrows here. So if you just take a look at these aces, 2 aces are in the middle, and there is no intersection between them and A2, which is the jack and 10 that I circled at the left, and also the number between 3 and 7 we circled at the right. There is no intersection between them. They are totally mutually exclusive. And also, if the replacement is allowed, then the selection of one cannot affect the second one and third one. So because of that, because over here we have not any replacement, so the first selection can affect the second one, and the second one can affect the third one. We expand the formula for the multiplicative rule when we have 3 actually events. Then the probability of their intersection will be the probability of the first one, A1, times probability of the second one given the first one, means that in a condition that the first one is occurred, times probability of the third one when the first and second one, and I said it, and the second one has been occurred. So because of that, we have this probability. The probability of A1 was given before. We calculated 2 over 52. But for the second one, we assume that the A1 is given, means that one card is already removed, has been already removed from the deck. So when we just remove that card, means that there is no aces anymore over there. We select one of them. So the remained cards will be 51. It's not 52. And the result, the probability of that cases, means that A2 will be 8 over 51. And the third one is 12 cases. But right now, when A1 and A2 has been occurred before, and we have this information, so the number of the cards becomes 50, and the result will be 8 over 5,525. So you can see that in this question, how can we use the extended multiplicative rule? So at the end, I just show you the third example about these things, and later on in the next lecture we will solve this example. We have a lot of things with the coins and tossing the coins, so we will discuss about this example in the next lecture. As I said it before, as much as you solve the question and example, you get expert in that type of the things, and it can help you to understand the topics better. So thank you for your attention. In the next lecture we will discuss about the base rule, and also we will solve this example. Thank you.